Hello everyone, let's look at our code, and here we will use torch, and let's start with code parts. Okay, let's scroll. Okay, so this is the class that defines a single dynamic layer. We are calling it dynamic layer, and it's built on top of PyTorch NN module, so we inherit from that just like we could for any custom layer. The idea here is that this layer is not fixed. It can be reconfigured during a runtime. That means we can change things like the number of output neurons, the activation function, or even the dropout rate later on without rebuilding the whole model. Now, in the constructor, this init function, we are passing 4 arguments: the input size, output size, the activation function name, and an optional dropout rate. If no activation is given, we default to value and dropout defaults to 0. Okay, we initialize a standard linear layer using an linear, then store the name of the activation function, and if a dropout rate is provided and greater than 0, we also set up an dropout. Otherwise, dropout is just set to none. That way we avoid unnecessary layers when not using dropouts. Down here we are initializing weights. What's happening here? If the activation is value or something similar like leaky value or ALU, we go with chimic initialization, which is typically better suited for value type activations. Otherwise, we fall back to Xavier initialization, which works well for 10H and sigmoid. Then finally, we just zero out to bias values. That's okay. Now, let's look at the forward pass. First thing we do is push the input through the linear transformation, just a regular matrix multiplication with bias added. That gives us raw output from the layer. Then, depending on which activation function we have selected earlier, we apply that to the output. So, for example, if we passed in value as a string earlier, we apply f.value x here. Same goes for 10H, sigmoid, leaky value or ALU, and if linear is selected, we skip activation entirely. No transformation is applied in that case. And once that's done, we check if dropout is active. If it is, we apply it here. If it is not, meaning dropout was set to none earlier, we just skip it. In the end, we return the final tensor after all of these operations. So that's how one layer behaves during a forward pass. Okay, let's scroll and stop. Now, let's say we want to make changes to this layer on the fly. For example, maybe we want to change the activation function halfway through training or update the number of output neurons. That's what this reconfigure method is for. We can update the activation function, the dropout rate, or the number of output features. If any of these parameters are passed in, we update them. If something is passed as none, it means we want to leave it as is. Okay, and for the dropout, it follows the same logic we used earlier. If it is greater than 0, we create a new dropout object. If not, we disable dropout entirely. Now the important part is here. If we have requested a new output size and it is different from the current one, we create a new linear layer with the new size, but we keep the same input size since that doesn't change unless we are modifying an earlier layer. Then we initialize the new weights the same way we did before. Chiming for value like activations and Xavier for the rest. Biases are reset to 0, 2. That's okay, and here's a nice touch. We copy the old weights and biases into the new layer as much as possible. So for example, if we shrink the layer, we keep only the first few neurons. If we expand it, we preserve the existing ones and let the rest be randomly initialized. And that helps us keep learning stable when resizing a layer. And here the step is actually replace the old layer with the new one. So once we have initialized a new linear layer, copy it over what we can and reset the rest, we just assign it back to self-linear. That's it. Now the layer has been updated and will behave according to the new settings. Okay, and we have a new class here. Alright, now we are stepping up from a single layer and looking at a full network structure. This class is called dynamic neural network. It's a basic neural network, but the key is that it's modular. You can add, remove, or change layers while it's running. In a constructor, we just initialize a few things. First, we store the input size, then we create an empty module list to hold the hidden layers. And finally, we define self-output layer, but leave it as none for now, since might not want to add the output layer immediately. And okay, let's look at how we add a new layer to this network. The method is called addLayer here, and we pass the output size, activation function, and an optional dropout rate. If we haven't added any layers yet, then we take the input size from the original model input. Otherwise, we just grab the output size of the last layer we added. Okay, then we create a new dynamic layer with the appropriate input and output size and store it in our layer list. It returns the index of the layer we just added, which can be useful later if we want to modify it. Okay, and that's done. Let's continue. Now for the output layer. This is handled separately using add output layer. Logic here is nearly the same. If we have no hidden layers, we use the network's input size. Otherwise, we use the output size of the last hidden layer. We create the output layer using our dynamic layer again and store it in self-output layer. Simple as that. And modifying part is here. Okay. So this lets us change the output size, the activation, or the dropout rate of any layer we have added. All of these are optional. If you leave something as none, it won't be touched. We call reconfigure on the target layer and it handles all the internal changes, including transferring the weights. But here's the important part. If we change the output size of a layer, we have to make sure the next layer in the sequence still works. That means it has to accept the updated output size from the layer before it. So we check if the modified layer is not the last one. If there is another one after it, we rebuild that next layer with the new input size and keep its existing output size and activation. Basically, we reconnect it properly. And same thing for the output layer. If we have modified the very last hidden layer and the network has an output layer, we rebuild the output layer to match the updated size. That way everything stays in sync and the shapes all line correctly. And let me scroll and stop here. Now, sometimes we might want to remove a layer altogether. That's what remove layer handles. We pass in the index of the layer we want to delete. First, it checks if the layer we are removing is not the last one. If it is not, we rebuild the layer that comes after it and we connect it to the one that comes before the removed layer, so the chain stays intact. But if we are removing the last hidden layer, then we need to reconnect the output layer instead. Same idea, we check the output size of the layer that will now come just before the output layer, and we rebuild the output layer with that size. And we just delete the layer from the list. Okay, so that's how we can dynamically strip out layers from the network without breaking everything downstream. And let me scroll. Okay, let's stop here. Alright, now we are looking at the actual forward pass of the entire dynamic network. This is handled by the forward method here, and what we are doing here is just looping through each layer we have added and applying it one after another to the input. We keep updating X as we go. If we have defined an output layer, we run that last, and finally we return the result. That's pretty much the full forward flow. That's okay. And next here is a simple utility get parameters. This just sums up the total number of trainable parameters across the whole model. So anything that's marked as requiring gradients is counted here. This is useful if we want to log the size of the model or compare different versions later. And cloning part is here. Okay, what's happening here? The clone method. This creates an exact copy of the network. Same structure, same weights. The way we do that is by initializing a new dynamic neural network with the same input size. Then we go through all the layers we already have and add the same ones to the new network and copy our weights and biases. If a layer has dropout, we preserve that too. We do the same thing for the output layer if it exists. That way we end up with a full clone that behaves just like the original. Okay, and I hope that's done for you, and let's continue. Now we are switching out to a new class. This one is called growing shrinking network. What is that? The idea here is to take our dynamic network and allow it to be changed programmatically during training, so we can grow or shrink the network structure based on performance or other criteria. And in the current structure, we passed in a base network and optional metric function. This metric function is what we'll use to evaluate performance, like validation loss or accuracy. We also keep a history list so we can track changes and possibly roll back. Okay, and let me scroll a bit, and here is the evaluation method, evaluate network. Pretty straightforward. It checks whether a metric function was given. If not, we throw an error. Otherwise, we apply the metric function to the network and return the result. We will use this to decide whether changes to the architecture actually improve performance. And another method is here, grow network. This method adds a new layer to the current network, but before doing anything, we make a clone of the existing network. That way, if something goes wrong, we can always roll back. We can choose where to insert the new layer. By default, we add it before the last layer. If we pass random as the position, it picks a random point, or we can give a specific index. And that's okay. As for the size of the new layer, we can set it manually, but if we leave it as none, the code figures out a reasonable value based on surrounding layers. If we are inserting it at the very beginning, it averages the input size and the first layer's size. If we are inserting near at the end, it uses the last hidden layer and the output layer. For anything in between, it just averages the size of the layers before and after the insertion point. That's okay, and once we have figured out the layer size and position, we start building a new version of the network. And first we copy overall the layers up to the insertion point, we preserve their settings and their weights, then we add in a new layer, and finally we copy the remaining layers after the insertion point. And weights and bases are cloned for every existing layer, so we don't lose anything. If there is an output layer, we also bring that over and keeping aligned with the updated structure. We store the previous network in history labeled as a grow operation, and we assign the new version back to self network. Okay, and that's it. Let's continue. Okay, the method is called shrink network. Basically, it lets us remove one of the layers. If we don't specify which layer to remove, it defaults to the smallest one, meaning the one with the fewest output units. And what's happening? We start by checking that the network has more than one layer, because if there's only one, we obviously can't remove anything. Then, as usual, we clone the current network so we have a backup in case we need to roll back. If no specific index is passed, we compute the size of each layer, pick the one with the smallest output size. This is just a basic heuristic. You could swap this method something smarter later, like saliency or gradients norms. Okay, that's okay. And once we know which layer to remove, we start building a new network. We copy every layer except the one we are removing. For each layer we either use the input size from original model, or if we are past the first layer, we use the output size of the previous one. If we are copying the layer that comes right after the one we removed, we adjust its input size so that it matches the output of the previous layer. That way the dimensions are still compatible, and for that specific layer we reinitialize weights instead of copying them, just to be safe. The others keep their weights as is. And of course, if there is an output layer, we reconnect it to the last remaining hidden layer, and since the shape might have changed, we reinitialize the output layer instead of transferring the weights directly. Once everything is copied and rebuilt, we log the operation into the history as a shrink step. Okay, and then assign the new network to our main reference, and we return that updated network. Now let's say we want to make a layer wider. That's where the within layer method comes in. It takes in the index of the layer we want to widen and new number of output units. First thing we check is whether index is valid and whether the new width is actually larger than the current one. If either condition fails, we raise an error and stop. If everything looks fine, we clone the current state, then call modify layer to apply the size update. And just like before, we'll log the previous version in our history in case we need to undo it later. On the flip side, we can also make a layer narrower using narrow layer. It is the exact same structure as widening. The only difference is that the new width has to be smaller than what it was before. We still validate index, check the size rule, clone the current network, apply the modification, and store the old version in case we want to reverse the change. And speaking of reversing, let's look at undo last change. This method simply pops the last saved version of the network from history and replaces the current one with it. If there is nothing to undo, we print a message and leave the network unchanged. Otherwise, we print out what we are doing and roll back to that previous version. So this gives us some flexibility during experimentation or tuning. And let's scroll. Example time. Okay. Alright, to wrap it all up, let's walk through this example script at the bottom. This gives us a quick demo of how to actually use dynamic neural network class in practice. And first we create a new network for something like minutes, and so we set the input size to 784 since that's 28 by 28 flattened, and we will later output 10 classes. Okay, and then we add two hidden layers. The first one has 128 units, the second has 64. Both of them use value and have dropout set to 0.2, nothing unusual there. Next we add the output layer with 10 units and use linear activation. That's because we will typically pair this with something like softmax in the loss function like cross entropy. And after setting up the layers, we print the total number of parameters that includes weights and biases in every layer. Then we loop through each layer and show its input and output sizes along with the activation it uses. Same thing is done for the output layer. So at this point, if you look at the printed out, we can see the network has parameters is here. That makes sense given the shape of the layers. Now and comes the dynamic part. We modify the first layer, layer 0, and increase its output size from 128 to 256. Then we print the architecture again. And as expected, now the total number of parameters has gone up. In fact, it almost doubled to a bit over what is that, 218,000. And if you look at the layers again, the first one now maps from 784 to 256, then 256 to 64, and finally the output layer remains unchanged at 64 to 10. So that's the full cycle. Create a network, build up layers, inspect its structure, and make live changes to it, all while preserving weights and letting the system adjust as needed. Pretty handy if you are experimenting and want some flexibility without starting from scratch each time. And thank you for listening. See you in the next class.